Howdy Ags! In this mini lecture, we will discuss fossil fuels as an energy source. Specifically, we will discuss coal, natural gas, crude oil, oil sands, and other types of fossil fuels. After reading chapter 19, watching this video, or reading the transcripts that go with this video, and watching the other assigned videos and activities for this chapter, you should be able to identify energy sources we use, describe the origins and nature of major types of fossil fuels, explain how we extract and use fossil fuels, and evaluate peak oil and the challenges it may pose. We use energy in our homes to power machinery, to drive vehicles, and to provide comfort and conveniences. For the most part, countries rely heavily on crude oil, natural gas, and coal for their energy. These three sources are the three main types of fossil fuels. Fossil fuels are carbon-based fuels that are highly combustible. Fossil fuels are formed from the remains of ancient organisms buried underground and subjected to the forces of temperature, pressure, and time. You'll notice from this table that crude oil, natural gas, and coal that crude oil, natural gas, coal, and nuclear energy are all non-renewable energy sources, meaning these sources take millions of years to develop. Once we exhaust these resources, there will be no more of these types of energy sources available. The other type of energy sources that are used to a lesser degree include solar, wind, hydroelectric, biomass, geothermal, and tidal and wave energy. All of these sources are renewable. The lessons of this week will focus on fossil fuels. We will soon be discussing the conventional and new energy alternatives to fossil fuels as they are described in chapters 20 and 21. Oil, coal, and natural gas supply 82% of the U.S. energy demand. So it is clear we are heavily dependent on a limited and non-renewable resource. As can be seen in the table at the top of this slide, some countries have more natural reserves or non-renewable fossil fuels. Some regions have sustainable reserves of oil, coal, and natural gas, whereas others have very few. Half of the world's proven reserves of crude oil lie in the Middle East, which is also rich in natural gas. Russia has the most natural gas, and the United States possesses more coal than any other country. You'll notice Venezuela has the most oil reserves, followed by Saudi Arabia and then Canada. Look closely and you'll see an asterisk next to Canada and Venezuela in the oil category. This is because their oil reserves are from oil sands, which is harder to extract than crude oil. The figure on the left shows the total energy of the United States. Notice that the thicker bars represent larger amounts. So you can see we import a lot of oil and we use that for transportation and to a lesser degree industrial purposes. We import less natural gas and even less coal. Recall that the U.S. has more coal than most other nations. What I want to draw your attention to is the fact that renewables, in the green at the bottom, represent a much smaller portion of our energy budget than any other source of energy. Also notice the tan arrows to the right of the boxes that represent transportation, industrial, commercial, residential, and electricity generation. These tan arrows represent the energy that is lost or wasted. Imagine how much we could reduce our energy demands if we could eliminate or minimize this lost energy. The graph on the right is the annual global consumption of fossil fuels. It should come at no surprise that fossil fuel consumption has increased drastically over the last 60 years. Though we once relied on more coal, though we once relied more on coal, oil has been the leading energy source for the globe since about 1965. What many people do not realize is that we cannot simply get energy for free. We must locate, extract, process, and deliver the energy we need. All of these things can be considered investment energy. It is important to understand that the amount of energy that remains after the investment energy is accounted for, this amount of energy that is left over is called net energy, or the difference between energy returned, or in other words, the amount of energy you got out of the resource, and the energy you invested in getting that energy out of the resource. Therefore, net energy equals the energy returned minus the energy invested. We can evaluate each energy source using a principle called energy returned on investment, or EROI. The EROI are ratios that are calculated by dividing the energy returned by the energy invested. In other words, EROI tells how much energy we receive per unit of energy we put into the process. Higher EROI ratios mean we receive substantially more energy than we invest. Lower EROI ratios mean we receive less energy per unit of energy we invest. For example, the EROI for oil was very high in the 1920s, but it began to decline after that because we extracted more of the resource. As we extracted more of a resource, there's less available to extract, and therefore we have to invest more energy to get that oil. In the 1920s, we could drill an oil well and oil would spontaneously shoot to the surface because of the high amount of pressure it was under. Well, we have extracted all of the easily accessible oil, so now we have to put more energy into getting oil out of the ground than we did in 1920. So you can see that the EROIs can change over time. In the 1950s, in the US, oil EROI ratios were 30-1. In the 1970s, it dropped to 20-1, and today that value is 11-1. EROI ratios can increase as technology improves. The call out in the graph in this slide illustrates that because the EROI increases after 1980 and again after 1990. These increases are attributed to the advanced oil extraction techniques made possible by technology. Not surprisingly, industrialized nations use up to 100 times more energy per person than developing nations. This figure shows that wealthy industrialized nations typically consume more energy per person than less wealthy countries that have not yet industrialized. For example, the United States has only 4.4% of the world's population, but it consumes 19% of the world's energy. As was mentioned before, fossil fuels formed from ancient organic matter. Specifically, these fuels formed from organisms that lived 100 to 500 million years ago. The energy in fossil fuels originally came from the sun because the organisms that formed fossil fuels were ancient autotrophs. The carbon contained in these ancient primary producers became concentrated over time as the tissues of the organisms decomposed and were compressed. Most organisms go through aerobic decomposition after they die because they are exposed to air, bacteria, and other organisms that break down their bodies and tissues. However, fossil fuels were produced by ancient organisms that underwent anaerobic decomposition, which is decomposition that occurs when there is little to no oxygen. The fossil fuel produced depends on a number of conditions at the start and throughout the process. Specifically, 1. Chemical composition of the organism. 2. Temperature and pressure to which it's subjugated. 3. Presence or absence of anaerobic decomposers. And 4. Passage of time. This figure provides an accelerated timeline to show how the three main types of fossil fuels develop. The first step in the process is that the organisms, such as woody vegetation, phytoplankton, or zooplankton, fall into a low oxygen environment, such as a lake, a swamp, or a shallow sea. The tree drifts to the bottom of the lake and is buried by sediment. The phytoplankton and the zooplankton drift to the bottom of the seafloor and are buried. The organic matter from the tree, phytoplankton, and zooplankton undergo slow anaerobic decomposition and become buried deep under sediment. This is the process by which kerogen is formed. Kerogen is the complex mixture of hydrocarbons, and hydrocarbons are compounds composed of hydrogen and carbon. Kerogen serves as the main source material for natural gas and crude oil, as well as some forms of coal. Heat and pressure transform kerogen to oil, natural gas, and some forms of coal. Notice that plant material, represented by a tree, is seen on the left side of the figure. This is because coal forms from plant matter that is compacted so tightly there's little decomposition. On the right side of the figure, you see phytoplankton and zooplankton. These soft-bellied sea organisms eventually form natural gas and crude oil. In all cases, the ancient organisms must be subjected to geothermal heat and pressure to transform into fossil fuels. We will now examine each of these three main types of fossil fuels independently. Coal is the most abundant fossil fuel on Earth. Coal was created 300 to 400 million years ago in swampy environments. It is a hard, black substance formed from the compression of ancient woody vegetation. The amount of water and carbon content and the amount of potential energy varies between different coal deposits. This figure illustrates that various types of coal, how they were formed, their water content, and their potential energy. The first substance you see listed on the left is peat. Peat is an organic material that is broken down anaerobically, but is generally wet, close to the surface, and not well compressed. For these reasons, peat has far less energy than coal. However, if peat is subjected to additional pressure, heat, and time, it will turn into coal. Scientists classify coal into 4 different types: lignite, subbituminous, bituminous, and anthracite. Lignite has undergone the least amount of heat and pressure, so it consequently has more moisture and less energy compared to other types of coal. Anthracite coal has undergone the greatest amount of pressure and heat, so it has a low amount of moisture and high condensed carbon content. This type of coal, therefore, has the most potential energy. If coal is near the surface, it is extracted using strip mining, which is when heavy machinery scrapes away massive amounts of land to reveal coal deposits below. Subsurface mining is used to extract coal that is deep underground. With subsurface mining, deep vertical shafts are dug and networks of horizontal tunnels are created through powerful blastings using explosives. A final way coal is extracted is through mountaintop removal. We will discuss this method in the part 2 video. Crude oil, also known as petroleum or black gold, is a sludge-like liquid mixture of hundreds of different types of hydrocarbon molecules. Natural gas consists mostly of methane, which is CH4. There are some other volatile hydrocarbons in natural gas. Crude oil and natural gas formed when dead organic material was buried in marine sediments and transformed by heat, time, and pressure. The organic matter was turned into kerogen, and kerogen was then formed into natural gas or crude oil when acted upon by heat, time, and pressure. Natural gas is found at 1.9 miles below the surface, and crude oil is found at about 1 to 2 miles below the surface. The map of the U.S. here illustrates where the national natural gas deposits are located. Notice Texas is a prime location for gas production. Oil and natural gas are extracted by drilling holes deep into the ground to reach these deposits below. If oil is under pressure, it will rise to the surface through the hole naturally. However, if the pressure has been relieved, it will need to be pumped out. Oil that comes to the surface naturally is the easiest to capture. After we capture that, we have to work much harder to extract oil or gas from the ground below because the pressure is lost. Note, it is a common misconception that dinosaurs formed fossil fuels we use today. Most fossil fuels are from ancient woody plants and algae, so T-Rex is not in your gas tank. A lesser known type of fossil fuels are sand oils and oil shale. Recall I mentioned earlier that Canada and Venezuela both have a great deal amount of oil sands. Specifically, Canada has the third largest proven oil reserves, but these reserves are oil sands. Oil sands, also known as tar sands, are layers of sand or clay saturated with a viscous, tarry type of petroleum called bitumen. The bitumen can vary between 1 and 20% in the clay and sand. Bitumen is a form of petroleum that is rich in carbon but poor in hydrogen. Oil sands are essentially crude oil deposits that have been degraded by water erosion and bacterial decomposition. Some people think that the oil sands of Canada are the answers to our continuing our current fossil fuel-based lifestyles and our dwindling supplies of oil. Others think that extracting the oil from the oil sands is an appalling pollution that perpetuates our dependence on fossil fuels and even greater threatens Earth's climate. Consider this fact as you contemplate where you stand on this issue. The EROI for oil sands is estimated to be between 1.5 to 1 and 9 to 1, with most estimates being between 3 to 1 and 5 to 1. Compare that to the EROI of oil, which is currently 11 to 1, hydropower, which is 10 to 1, and wind, which is 23 to 1. In order to get the oil sands, the boreal forest under which they sit must be cleared and the area must be strip mined. The sands are mixed with hot water and chemicals, creating toxic wastewater. The Canadian oil sands produce 1.7 million barrels of oil a day. We, the United States, are the major purchaser of this oil. There is a major national debate over the pipeline that transports this oil from Canada to the U.S. This pipeline is called the Keystone Pipeline. The existing pipeline has limited capacity, and for many years, the Trans-Canada Corporation has pushed to build an extension called the Keystone XL extension to deliver more oil at a faster pace to ports as far south as South Texas. As with most issues, the Keystone XL extension has staunch proponents and opponents. Among other things, the proponents want the jobs the pipeline would create. The opponents dislike the destruction of the boreal forest in Canada and the potential for oil spill over the Ogallala Aquifer in the United States. Part of the activity this week will be related to this pipeline project. Oil shale is sedimentary rock that is filled with kerogen. Oil shale can be processed to produce shale oil, which is a type of petroleum. Oil shale forms when kerogen was not buried deeply enough or was not subjected to enough heat or pressure. It is important to note that oil shale is not related to shale gas. Shale gas is another name for natural gas, and that gas is generally extracted using hydraulic fracturing. It is estimated that 65% of the world's shale resources are located in northwestern Colorado, northeastern Utah, and southwestern Wyoming. Oil from oil sands are extracted in two processes. If oil sand deposits are near the surface, they are extracted using strip mining. For deep oil sand deposits, we drill down and inject steam and solvents to liquefy and isolate bitumen in place and pump it out. Once extracted, oil shale can be buried directly, like coal, or can be baked into the presence of hydrogen and in the absence of air to extract liquid petroleum. The reasons why crude oil has its name is that in its natural and purest form, it has very little use to us. Crude oil must be refined to get the various fuels we use, such as gasoline, kerosene, and diesel. The process of refining crude oil produces a variety of fuels. Crude oil is a complex mix of hydrocarbons. Different petroleum products can be made if the hydrocarbons are separated. The hydrocarbons have carbon chains of different lengths. The length of the chain determines the molecule's properties and use. The simplest way to look at this is that the longer the chain, the more energy the fuel has. Refining is the separation of hydrocarbons based off of size and chemically transforming them to create specialized fuels for many uses. In addition to fuels, refining can also produce lubricating oils, asphalt, and plastic precursors. Crude oil is refined by boiling it. As it's boiled, the hydrocarbons volatilize and float upward through the distillation column. The image on the right shows the different types of crude oil products produced at various temperatures, and the barrel on the bottom shows the percentage of each major category of product that is typically generated from a barrel of crude oil. It is important to note that although there may be more fossil fuel deposits, they are not all feasible to extract. However, technology advances are enabling companies to access some of the more difficult to extract fossil fuels. This means that with technology, the amount that is technically recoverable increases. While technology limits what can be extracted, it is economics that determines how much will be extracted. Some fuel is so hard to extract that it is not worth the cost. As the price rises, however, economically recoverable amounts approach technically recoverable amounts. This leads to the term proven recoverable reserve. This is the amount of oil or any other fossil fuel that is technically and economically feasible to remove under current conditions. Fossil fuels have many uses. Cultures have used fossil fuels for centuries. Ancient China, the Roman Empire, and the Hopi Nation are all known to have used coal. Coal helped drive the Industrial Revolution. One of the first uses in this revolution was to fuel furnaces to produce steam. Coal is used to generate electricity. We burn coal to convert water to steam. The steam turns a turbine, which in turn generates electricity. This can be seen in the figure from your book of a coal-fired power plant that is featured here. We now have clean coal technologies that help to filter out the pollutants from the combustion process. Clean coal processes collect toxic ash residue and dispose it at a hazardous waste disposal site. Natural gas is versatile and clean burning fuel. Per unit energy produced, it emits half as much CO2 as coal and 2/3 as much as oil, meaning that natural gas burns much cleaner than coal. Natural gas is used to generate electricity, heat homes, and cook food. You may have heard of liquefied natural gas, or LNG. LNG is gas converted to a liquid at low temperatures. Because it produces less carbon emissions than coal, natural gas is viewed as the bridge fuel, because it could serve as a bridge from a switch from a fossil fuel-based economy to a renewable energy-based economy. The United States and Russia lead the world in production and consumption of natural gas. In this table, you see that China is the primary producer and consumer of coal. Coal provides 40% of the United States' electrical generating capacity. Our modern fossil fuel-based economy began in Tutsville, Pennsylvania, when the world's first oil well was drilled in 1859. Today, the world produces and uses nearly 200 gallons of oil each year for each person on the planet. Oil is mostly used for transportation. However, technology has advanced to the point that we are now able to use oil to make a wide variety of products, including plastics, lubricants, fabrics, and pharmaceuticals. Though we in the U.S. compose 4.4% of the world's population, the United States consumes 1/5 of the world's oil. We can expect difficult decisions and conflicts in the near future regarding fossil fuel resources, as the industrialization in China and India is increasingly driving demand for fossil fuels. As has been mentioned before, fossil fuels can be refined to create petroleum-based products. Look around your room or any place you spend time indoors and you'll see petroleum products everywhere. They are in fabrics we wear, the materials we consume, such as the waxes on food, the pharmaceuticals we take, and other products we use every day. We are gradually depleting our fossil fuel reserves. Current estimates indicate that there is slightly more than 1 trillion barrels of proven conventional reserves left. If you add the oil sands of Canada and Venezuela to these reserves, we can get to about 1.6 trillion barrels or more. We have used 1.1 trillion barrels of oil, almost half of our reserves. The reserves to production ratio, or RP ratio, is the amount of total remaining reserves divided by the annual rate of production, i.e. the extraction and processing. At current levels of production, which is 30 billion barrels of oil per year, we have about 54 years of oil left. Using the RP ratio, natural gas reserves would last 64 more years and coal would last 112 more years. The true number of years left for each fuel may be different than predicted by the RP ratio. It may be less since our demand and production have been increasing. Or it may be more as technology and prices increase and we find more proven reserves. For example, mining of oil sands has increased reserves. But here's the kicker. We will face a crisis not when we run out of oil, but when the rate of production comes to a peak and begins to decline. In general, production of a resource declines once reserves are depleted halfway. Past the peak, if demand holds constant while production declines, a shortage occurs. This gets us to the key concept of peak oil, which is when the rate of oil production peaks and then declines. In 1956, Shell geologist M. King Hubbard predicted that crude oil production in the U.S. would peak around 1970. This production is called Hubbard's peak. As you can see from the graph on the top of this slide, Hubbard's prediction proved to be accurate. The U.S. oil production peaked in 1970. Since then, Alaska, the Gulf of Mexico, and secondary extraction has declined. The curve shifts to the right as more oil is discovered. Today, U.S. oil production is spiking upward as deep offshore drilling and fracking make new deposits accessible. Hubbard also analyzed data and predicted that global oil production would peak in 1995. As you can see from the graph on the lower portion of the slide, global oil production is still growing. However, much of this growth is due to advanced technology to extract alternative oil reserves, such as oil from tar sands, deep water, or tight formations. So while oil production is still growing at the moment, many scientists predict peak production in the next decade. This is due in part to the fact that discoveries of new oil fields peaked 30 to 40 years ago. In summary, we are using more oil than we are discovering. Each discovery of new oil sources delays the peak by increasing proven reserves. Some analysts believe we will continually find new sources. Such people are often referred to as cornucopians. Others believe that our supplies are dwindling and that we are approaching or have already reached peak oil. These people are often referred to as peakists. However, predicting the exact date of peak oil is very difficult due to a variety of complicated factors. Richard Heinberg wrote the book Snake Oil: How Fracking's False Promise of Plenty Imperils Our Future, and he distills down the data from a variety of national agency and peer-reviewed studies to discuss the true nature and depth of fossil fuel dependency problem. He describes 4 things that complicate the prediction of peak oil. These are: 1. There's a difference between reserves and resources. Reserves are defined as the total fossil fuel endowment that is extractable at realistic market prices and with current technology. Resources, however, are the total fossil fuel endowment. So you can see that although there may be resources available, actually locating, extracting, and processing them may be cost prohibitive, or we may lack the technology to do so. 2. New discoveries, such as very deep resources. We have new discoveries, such as very deep resources, such as deep oil that we get deep below the surface of the sea. However, data indicates that on average, the oil industry finds 1 barrel of oil for every 4 to 5 that we use. The global peak rate of discovery occurred in about 1960 and has been declining since. 3. Wildcards such as politics, technology, and the economy can complicate the prediction of peak oil. 4. The International Energy Agency's definition of oil includes natural gas liquids. Also, some countries are a bit loose as to what they define as domestic oil. Sometimes they include imported oil in their calculation, which obviously will skew the data. Furthermore, some agencies include biofuels, which is made from agricultural products, in their definition of oil. So those are the things that complicate the prediction of peak oil. The issue of peak oil gets even more complicated. Companies and governments do not disclose the amount of their oil supplies. There is also a disagreement among the geologists about reserves. The U.S. Geological Survey estimated twice the proven oil reserves as earlier estimates. But one thing that we do know is that peak production will occur and our lives will be profoundly affected. Experts studying peak oil indicate that actual peak oil production will probably occur over several years, and the decline of the peak will continue for decades. So what are some of the impacts of passing peak oil without having developed renewable energy resources? 1. We are expected to experience what's called the long emergency, which is when we lack cheap oil to transport goods. Consequently, our economies could collapse and become localized. 2. Large cities could not be supported without urban agriculture. 3. Fewer petroleum-based fertilizers and pesticides would mean increased hunger if we have not found alternative ways of growing high-yield quantity of food. 4. Suburbs will be hit hard due to reliance on cars. More optimistic observers argue that as supplies dwindle, conservation and alternative energies will kick in and we will be saved from major disruptions. If this subject of peak oil interests you, I would recommend that you read Richard Heinberg's book, Snake Oil, How Fracking's False Promise of Plenty Imperils Our Future, or his other book titled Peak Everything, Waking Up the Centuries of Decline. This concludes the first mini lecture on fossil fuels. If you haven't already done so, please watch part 2. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline. Thanks and Giga.